I've started recording.
Hey, can you see the book?
Yeah.
Yes.
Cool. Okay.
Can you like zoom in? Stop.
So, oh yeah, sure. This. This book. Okay. So I was thinking that we could maybe start from like do things a little bit differently. Like I've been told that Zetili is a relatively easier book to go with. So we're not gonna give up on Sakurai, but like we're gonna take a break from it, and the stuff that we're studying from Sakurai, we're gonna try them in Zetili, is what I'm thinking. Because there's a lot of examples in it, and that would be good for us to like learn the stuff, learn the math behind all of it, right? Okay. So I'm just gonna get a pen and paper. I forgot. So we're gonna start out from chapter 2 of Zetili, page 95. So I assume you guys are on the page.
Yeah.
Mm-hmm.
So start reading. Who wants to read first?
I can read
Okay,
the first paragraph.
One of you? Okay, cool.
Yeah. Introduction. Mathematical tools for quantum mechanics. Introduction. We deal here with mathematical machinery needed to study quantum mechanics. Although this chapter is mathematical in scope, no attempt is made to mathematically complete or rigorous. We limit ourselves to those practical issues that are relevant to the formalism of quantum mechanics. The Schrödinger equation is one of the cornerstones of the theory of quantum mechanics. It has the structure of linear equation. The formalism of quantum mechanics deals with operators that are linear and wave functions that belong to an abstract Hilbert space. The mathematical properties and structure of Hilbert space are essential for a proper understanding of the formalism of quantum mechanics. For this, we are going to review briefly the properties of Hilbert spaces and those of linear operators. We will then consider direct breaker notation. Quantum mechanics are formulated in two different ways of Schrödinger and Heisenberg. Schrödinger waves mechanics and Heisenberg matrix mechanics are the representation of the general formalism of quantum mechanics in continuous and discrete basis system, respectively. For this, we will also examine the mathematics involved in representing ket spreads, brackets, and operators in discrete and continuous spaces.
Okay. Keep going.
Okay. 2.2, the Hilbert space and wave functions. The linear vector space. A linear vector space consists of two sets of elements and two algebraic rules. A set of vectors and a set of scalars, a rule of vectors addition and a rule for scalar multiplication. Additional rule. The additional rule has the properties and structure of a abelian group.
Just you guys know what abelian is, right?
Yeah.
Tell
Yeah.
me. It just means it has
Because
commutativity.
what I remember is that it's like they're commutative with every like one element or something like that.
Yes, it is commutativity.
Mm-hmm.
Yeah. Okay, continue.
And the vectors of a space, their sum is also a vector of the same space. So here we have two examples, commutative and associative. existence of a zero or neutral vector. For each vector, there must exist a zero vector such that the example is there. Existence of a symmetric or inverse vector. Each vector must have a symmetric vector. Yeah. Multiplication rule. The multiplication rule of vectors by scalars. Scalars can be real or complex numbers as these properties. So the first properties is the product of a scalar with a vector gives another vector. So in general, if there are two vectors of the space, any linear combination, it's also a vector of the space. A and B being scalars. Examples are below. Distributive with respect to addition, associative with respect to multiplication of scalars, and last but not least, for each element, there must exist a unitary scalar and a zero scalar.
Okay, cool.
Mm-hmm.
You want to take a break?
Up to you guys. Do you guys want to read?
Yeah, sure. I'll take a shot. The Hilbert space 2.2.2. A Hilbert space H consists of a set of vectors and a set of scalars which satisfy the following four properties. H is a linear space. The properties of a linear space were considered in the previous section. Yeah, I think I remember that still. H has a defined scalar product that is strictly positive. Scalar product of an element psi with another element pi is in general a complex number denoted by psi times psi comma phi, where psi comma phi equals to complex number. Watch out for the order. Since the scalar product is a complex number, the quantity this is generally not equal to that. Such that this is equal to, so psi comma phi equals to psi star phi, while phi comma psi equals to phi star psi. The scalar product satisfies the following property. Scalar product of psi with phi is equal to the complex conjugate of the scalar product of phi with psi. Wait, what? Oh, okay. Cool.
Mm-hmm.
Yeah. Okay, the scalar product of phi with psi is linear with respect to the second factor if psi equals to a psi 1 plus b psi 2. So okay, they just okay, cool. And antilinear with respect to the first factor if phi equals to a phi 1 plus b phi 2. I feel like we're slowly gonna be dealing with like stuff that like these formulas. I mean, I understand them, but they're a little bit complicated to remember. So it's gonna happen. It's gonna be like similar to what happened in differential geometry. Yeah. A phi 1 a phi 1 plus b phi 2 comma psi equals to a star phi 1 comma psi plus b star phi 2 comma psi. Scalar product of vector psi with itself is a positive real number. Psi comma psi is equal to this. Yeah, that's just a modulus square. The equality only holds for psi equals to 0. Like zero vector. It's just separable. Oh, there exists a Cauchy sequence. Psi n belonging to H n 1 2 dot 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 such that for every psi of H and epsilon greater than 0, there exists at least one psi n of the sequence for which psi minus psi n mod is less than epsilon. Oh, this is dope. You guys know Cauchy sequence? Have you guys studied real analysis?
Yeah, I studied it on my own. I vaguely remember this.
Yeah, I think it was taught in real analysis too.
How much have you studied on your own, Farmer? Like, You're in your first year, right?
Yeah.
Yeah.
I,
What the hell, man?
dude,
I didn't know this shit until you know they were they were taught to us in class.
I'm a CS major today in teaching this. Okay. Which so the idea is that it's basically just going to get closer and closer to the actual limits, right?
Yes.
Yeah.
Okay.
It's just limit.
Yeah, that's a. This is just a formal way to say it. Root analysis
Yeah.
stuff.
Yeah.
Oh, Zach is here too. Hi, Zach. H is complete. Every Cauchy sequence psi n belongs to H converges to an element of H. That is, for any psi n, the relation limit n comma m approaching infinity, psi n minus psi m mod is equal to 0, defines a unique limit psi of H such that limit n approaches infinity, psi minus psi n is equal to 0. Right, so it generalizes.
Yeah.
Cool.
Okay.
Remark. You should note that in a scalar product, phi comma psi, the second factor, psi belongs to the input space H, while the first factor, phi belongs to its dual input space Hg. Distinction between H and Hg is due to the fact that, as mentioned above, the scalar product is not commutative. The order matters. Fair enough. From linear algebra, we know that every vector space can be associated with the dual vector space. Excuse me.
What is a dual vector space?
Bro, you know the dual correspondence, right? We studied it in Sakurai.
Yeah.
Like something that multiplies with the ket, and like bra that multiplies with the ket and gives a like a number, complex number.
Yes.
Yeah.
But
Oh,
like,
same stuff.
is there like a general like definition we have for like a dual vector space in? Because it says that every
Yeah,
vector.
that's the definition. Like okay, so if there is an element, if there is a number, and there is a dual to it, so if you operate the dual with the, if you multiply the dual with the number, it gives a like well, okay, so it's not a number, it's a vector, right?
Yeah.
So if we multiply the dual of the vector with the vector, then we get a number, something like that. Not 100% sure. Does that make sense?
I think Zach sent a message that they covered double cover or the Born rule.
Sorry.
Zach sent a message in the chat.
Oh,
So I can do voice, but it might be a little bit loud. I'm out here at the motorcycle range. So what I was asking is, when you guys are talking about dual vector space, it sounds related to the Born rule and double cover. I just didn't know if you guys have covered those things yet up to this point, or if that's something that's coming later on in the chapters.
oh, we haven't covered it.
Okay.
I don't think so, at least. And
Cool.
I'm not even sure if they're related.
I didn't think so, but I just wanted to try to get some kind of like understanding where you guys were at.
I wouldn't cover it. I don't even know what that is.
So it relates to what I was saying to you about SU2 and SO3. SO3 is the
Yeah.
rotational around the SU2. Yeah. And
Yeah.
the double cover is where those two vector spaces have commonality. The Born rule is where you basically get two different values to get a probability metric.
Oh,
So this is basically setting us up for the Born rule and everything. That's why I was confused. That's why I was confused if you guys had covered it already. But I'm going to go back on mute.
yeah, you go back on mute. You're revealing too much of the mystery that.
Yep, like I said, I'm going on mute.
Okay.
Okay, cool. 2.2.3, dimension and basis of a vector space. Anybody else who wants to try reading? No,
I can
I already read. Okay, your turn.
Okay. Dimension and basis of a vector space. A set of n non-zero vectors phi 1, phi 2 to phi n is said to be linearly independent if and only if the solution of the equation, you have the equation, is a1 is equal to a2, all of them are equal to 0 till an. But if there exists a set of scalars which are not all 0, so that one of the vectors, say phi n, can be expressed as a linear combination of the others, phi n is equal to the sum from I equals 1 to n minus 1, ai phi I plus, again, we have the rest of the vectors.
Yeah.
The set phi I is said to be linearly dependent. The dimension of a vector space is given by the maximum number of linearly independent vectors the space can have. For instance, if the maximum number of linearly independent vectors a space has is n, i.e. phi 1, phi 2 to phi n, the space is said to be n-dimensional. In this n-dimensional vector space, any vector psi can be expanded as a linear combination. Psi is equal to the combination of all the other vectors phi I. The basis of a vector space consists of a set of the maximum possible number of linearly independent vectors belonging to that space. This set of vectors phi 1 to phi n, to be denoted in shorts by phi I, is called the basis of the vector space, while the vectors phi 1 to phi n are called the base vectors. Although the set of these linearly independent vectors is arbitrary, it is convenient to choose them orthonormal. That is, their scalar products satisfy the relation phi I comma phi j, so the scalar product is equal to the pro-negro delta ij. We may recall that delta ij is equal to 1 whenever I equals j and 0 otherwise. The basis is said to be orthonormal if it consists of a set of orthonormal vectors. Moreover, the basis is said to be complete if it spans the entire space. That is, there is no need to introduce any additional base vector. The expansion coefficients ai in 2.13 are called the components of the vector psi in the basis. Each component is given by the scalar product of psi with the corresponding base vector. Aj is equal to psi j psi. Examples of linear vector spaces. Let us give two examples of linear spaces that are Hilbert spaces, one having a finite set of base vectors and the other having an infinite basis. The first one is a three-dimensional Euclidean vector space. The basis of this space consists of three linearly independent vectors, usually denoted by I, j, k. Any vector of the Euclidean space can be rewritten in terms of the base vectors as a is equal to ai plus a2j plus a3k, where a1, a2, a3 are the components of a in the basis. Each component can be determined by taking the scalar product of a with the corresponding base vector a1, which is equal to I times I dot a, a2 which is equal to j dot a, and so on. Note that the scalar product in the Euclidean space is real and hence symmetric. The norm in this space is the usual length of the vectors, which is given. Note also that whenever a1i plus a2j plus a3k is equal to 0, we have a1 is equal to a2 is equal to a3 is equal to 0. That none of the unit vectors I, j, k can be expressed as a linear combination of the other two. The second example is the space of the entire complex functions psi of x. The dimension of the space is infinite, for it has an infinite number of linearly independent basis vectors.
Okay.
Okay.
Examples. Let's try to maybe not look at the solution, right? And try these questions at least, like maybe one or two. Let's try like a part, I suppose.
Yeah.
Okay, so first one is gonna be linearly independent, right?
Yeah, but what I'm questioning is how do we show that it's going to be?
We can like use the
Oh,
formula.
okay. Yeah, no, I just realized it's yeah. We just plug into formula and they're all like greater than zero, right?
Sorry.
We plug them
Yeah,
into the
yeah.
formula. They're all going to be greater than zero. I don't know. Like if we do plug them into the formula, how would we say that? Couldn't they have a non-zero solution?
Well, I am not sure if they need to be like greater than zero or anything. Like so basically, we have to prove that this equation is only zero if the coefficients are zero.
Yeah.
That's how I understand it.
Yes.
So in this case, because these functions, they can't even be added. So therefore, like for their sum to be equal to zero, yeah, that can only happen if uh, the coefficients are equal to zero.
Yeah.
I feel like that should be the straightforward logic,
Yeah.
but feel free to correct me.
But is that what I'm wondering? Is that enough? Is that all it's asking? I guess.
Sorry.
Is that all that's asking? Is that is that like enough?
Yeah, so it's asking whether they are linearly independent
No.
or dependent, right?
Oh no, what I was asking is that like is that
So,
enough to like show that as a proof?
I mean, they can try to like do something resembling a proof, I suppose. That would be nice. But like not like a proof, just like using the functions themselves,
Yeah.
you know. So it shouldn't be so bad. Uh, so this is how I've done it. If you guys can see it.
Okay. Yeah, that's what I wrote. It can only be zero if a1. Okay. I guess so. Yeah. That
Yeah.
should make sense.
It's not like I just feel like it should be. Well, I mean, we can always just check the solution.
Yeah.
Completely forgot about it.
I'm wondering if that's what they wrote. Is clearly.
First set is clearly linearly independent since this implies zero. Yeah,
Yeah.
good.
Okay. Good enough.
Yeah, and I think B part is the same. Like it's gonna be the same issue. C part will be anyone wants to guess.
Probably dependence. It's x and
Right.
5x.
Sorry.
We have x and 5x, so it's going to be dependent.
Yeah.
Yeah.
Yeah. D part. Anybody wants to try it or what?
1, 2.
It's a little bit messy.
Yeah, I think with that, that's going to be. You have to pick a 4x4, right? It's a 4, not a 4x4.
Oh.
It's like a 4x, like a 4x3.
Yeah. 4x3. Nobody wants to solve.
Yeah.
Yeah, they've already given us the solution, so they are not linearly independent. Yeah, I mean, this is a good exercise if we want to try like row reduction and find the what's it called, the dependence of one equation or the other.
Yeah.
So
The main thing.
Yeah.
It's called wrong skin matrix.
The what?
Oh, Ronskin.
Yeah,
It has.
Ronskin is like a concept from differential. Is it differential equations?
Oh,
it is. I think we can use wrongest matrix to check if it's linear independent or not.
Yeah, yeah.
Yeah, if it's complicated.
You can't use that.
Yeah,
Yeah,
wait,
but
what?
like
that's like
you know
a
what?
brute force way.
Wait, what's the Ron scan?
Okay.
uh, wrong scheme. It's the determinant of the function. So we have like fx, gx, and hx, right? So um, we take the derivatives, first derivative and the second derivative, and put them into a 3 by 3 matrix.
Mm-hmm.
And we take the determinant of it if it's um,
Bro, I
if
just
it's
typed
not
it out.
identical to 0,
Oh.
the function is linear independent. If it's identical to 0, then it's not linearly independent. So if the equations get too complicated, we can use the Wronskian matrix to check if it's dependent or not.
Oh, okay. Okay.
Yeah.
Yeah. Let me check that out.
Nice. I wrote out the spelling of Ronskin in the chat so that
Yeah.
you don't
Okay.
get confused.
Okay.
Yeah.
Thank
It's
you.
like the safest way, but brute force way to check something is
Yeah.
dependent or not. Yeah.
And they don't teach us that like early on, which is kind of sad.
No. They expect you to know it, I think.
Anyway, following set of vectors in 3D Euclidean space linearly independent or dependent. Okay, you guys want to do this?
This is just like
I mean, all we have. Sorry,
I was saying that this is just gonna be row reduction, right?
let's just what?
Row reduction.
Yeah, wrote
Yeah.
it.
Yes.
Yeah. So, like for example, for part A, will just be like
Independent.
we remove the negative from -1, and we divide the -2 by 2 and -2 and -1 and 3 by 1, and we get a linearly independent. So if we get a matrix, then identity matrix, then we have a linearly independent.
Yeah.
I wasn't supposed to say the whole solution though. But
Okay. Yeah.
okay, he's doing it like algebraically.
Yeah.
If that's the correct one here. Yeah, but like it shouldn't be too hard. So let's just move on. Okay, part B. 2.2.4. You guys want to do more, or do you guys want to take a break for today?
I think
Have
I'm
a
good
lot
with
of
doing more. I'm good with doing more.
Want to do more?
Sure.
Yeah, sure.
Okay, then you read.
Oh, okay. 2.2.4 Square integrable functions, wave functions. In the case of function spaces, a vector element is given by a complex function and the scalar product by integrals. That is, the scalar product of two functions psi of x and phi of x is given by psi phi d is equal to the integral of psi conjugate of x times phi of x dx. If this integral diverges, the scalar product does not exist. As a result, if we want the function space to possess a scalar product, we must select only those functions for which psi phi is finite. In particular, a function psi of x is said to be square integrable if the scalar product of psi with itself, so psi which is equal to the integral of psi of x, absolute value, the mod is squared, dx is finite. It is easy to verify that the space of square integrable functions possess the properties of a Hilbert space. For instance, any linear combinations of square integrable functions is also a square integrable function, and 2.21 satisfies all the properties of the scalar product of a Hilbert space. Uh, Note that the dimension of the Hilbert space of square integrable functions is infinite, since each wave function can be expanded in terms of an infinite number of linearly independent functions. The dimension of a space is given by the maximum number of linearly independent basis vectors required to span that space. A good example of square integrable functions is the wave function of quantum mechanics, psi of RT. We have seen in Chapter 1 that according to Born's probabilistic interpretation of psi of RT, the quantity absolute value of psi of RT squared d cubed r represents the probability of finding at time t the particle in a volume d cubed r centered around the point r. The probability of finding the particle somewhere in a space then must be equal to 1. Okay, we have this equation here.
Yeah.
Hence, the wave function of quantum mechanics are square integrable. Wave functions satisfying 2.23 are said to be normalized or square integrable. As wave mechanics deals with square integrable functions, any wave function which is not square integrable has no physical meaning in quantum mechanics. Do we do like do we wanna like look at this again? I didn't really get this part of psi of RT, what we're doing here.
What did you say?
Do we like what were we doing here with psi of RT? I don't like for the wave function.
So here,
Yeah.
so bro, R is just the position vector, right? So
Yeah.
it's with respect to x, y, and z. So we're just integrating it with respect to x, y, and z on the like over the whole space. So the probability of finding the particle will be 1. I think. Yeah, that's what it says.
Okay.
Does that make sense?
Okay, so okay. So this is just like probability, right? So this is just represents the probability of finding this particle at any position. It makes sense. Okay, that its integral is gonna be then.
Yeah.
Okay.
Yeah. So when we are talking about the wave function, when we integrate it over a certain volume, in this case, the volume is the whole of space from negative infinity to positive infinity in each direction, then we get the probability of finding the particle in that space. Okay. And in this case, the probability will be 1 because we're checking the whole space.
Okay. And like, wait, why are we allowed to separate it based on x, y? Because this seems like we're only integrating with respect to z here, not x and y, right? You separate those components out, it seems.
That's true. I think that like the author just skips steps. First they'll do it with respect to z, then with respect to y, then respect to x. I hope so. Otherwise, otherwise it would just be
infinity times infinity.
Yeah, maybe. Not 100% sure on this. So
Yeah, I think you're right. It's true. X and Y.
Okay.
yeah, I don't know why they've written it like in a weird way. Like dx and dy should be behind dz, you know?
Yeah.
That would make sense.
That's what I was thinking as well.
Yeah,
Sure.
and
Maybe. 2.23.
yeah, I think one point to make is that you see this square integral a lot in signal processing and quantum mechanics. So for like Fourier series, you're gonna see it a lot too if you're gonna take it in the future. We use it because I think if I'm correct, the square integrals represent the amplitude of a wave, or a signal. So it's proportional to its intensity or the power density. Yeah.
Okay.
So
That makes
it's
sense.
good to know.
Mhm.
Okay.
Okay. Okay. I think we should stop here.
Yeah.
Direct notation, like we'll do next time. Direct notation, and the main goal of what I was trying to do today was the examples on bracket notation,
Mm-hmm.
because that's where we were in Sakura as well. That was like 2 weeks ago. Missed a bunch of time, but it's okay. We'll continue with this 2.3 direct notation, page 100. I'm just gonna write that down.
Sure.
And yeah, all right.
Okay.
Thank you guys for joining, I suppose. Good to see you. And Parmar, when you get a chance, send both the videos to
Yeah.
Zenith.
Yes, I'll send those over today.
Cool.
Any comments, questions, or doubts you guys have? Aspectero has been quiet.
I think we discussed pretty well.
Like this is the best that we can do while we're studying on our own. Like we don't have anyone guiding us, so we're learning by ourselves and we're learning from each other. That's like kind of the point. Otherwise, I wouldn't learn it. I would just be too lazy.
Okay.
Right.
Yeah.
I had like one question. So what exactly is psi of RC?
It's a wave function, bro.
So when we
So
say,
yeah.
what do we mean by like a wave function? Like what are we?
So a wave function is like an equation. Uh, if I recall correctly, I think it involves like E and stuff. There are different examples of it. Let me just check.
Like I know like
Example.
physically what it means, but not like really mathematically like what we're talking about.
Mathematically, it defines the probability with which you will find you will find the particle in a given volume.
Yes. Yeah, that's like
Yeah.
what I've heard like from my teachers, right? But I don't like when we're given that, right? So if I just am given that function, right? Am I actually like representing that? Like what is this?
Sorry, repeat again.
So I get that like it's so like for like an electron it gives the probability that we find that electron at a certain position, right? So however like that's given by I believe the integral, yes, of like absolute value of psi of RT squared.
Yeah.
Right. So when we have like a psi of RT on its own, is that like meaningful in a certain way, or is it just that where the integral representation is useful?
That's a good question. That's a very basic question that I don't know the answer to. But if I am if I can make a guess, um, wave function is just like a function, like it will determine the properties of the wave at any given time. And when we do an integral of the wave function, I think that is when we find something that we can measure. I think I'm not 100% like confident with that answer, and I think we should probably all look into it.
Yeah.
But like that's what I think.
Okay, yeah. I think
You're correct, I think. I agree with you there.
Can I please repeat the question?
Sorry.
Can you please repeat the question?
Okay, my question was that when we take the integral of psi of RT, the absolute value of that squared, right? We are basically saying we want to know the probability of finding like an electron in some region. What is the actual like physical meaning of psi of RT like on its own? What is that? Does that have a physical representation, or is just that the integral is what we're going to be using?
Okay. I'll look into it. Actually, I've studied that. I think it's. I will have to look on it, but I will clear that out.
Okay. Okay.
Hey,
So
anything
yeah,
else?
because
Yeah.
R is the position of vector in the space, right? So I think you're correct
Yeah.
for saying it's the gives you the probability density overall in the region if you integral.
What does probability density mean? Like that's like the PDF, right? The function, right?
Yeah.
Yeah. Just the integral, I think, over like limit. That's what PDF is, right?
Yeah, the phi square you were talking about, no?
Yeah. But for PDFs, we just use like the function itself. So I believe then the PDF would be just psi squared in that case, right?
Yeah.
I think I'll just wait. I'll like read chapter 1. I think that's probably gonna be best.
I think you have to read about the radial and angular part of the wave function.
The which parts?
That will be the best. The radial and the angular part of the wave function.
I heard
radial and angular parts.
Radial and angular. Okay.
Yeah. Actually, that covers the probability density.
Oh, okay. I'm gonna search that up. Yep.
That covers like that topic is in the atomic structure, I suppose. Schrodinger's wave equation, basically.
Okay. Okay. Thank you.
Yeah, we'll look into it, and definitely I think I'd like to recheck my answer on what the wave function actually represents beyond saying that it's just a function, because I don't think that's good enough for an answer. So yeah, that's homework for me. You guys can pick your homework as well, and yeah, let's meet again next Sunday. Yeah.
Cool. Yeah.
All right. See you guys.
See you guys.
Yep. Bye. Okay. I don't really like that answer. Do I? I'm